Bismillah ar-Rahman ar-Rahim. Today we are recording our 12th lecture on mechanics of materials. We have finished chapter 6 in the previous lecture. We solved two problems on the beam shear, and now we are going to start the last chapter, which is chapter 7, which is on transformation of stress and strain. So in this we will be talking about biaxial stresses. In chapter 2 we talked about axial loading, in which the loading was in one direction only, but now we are going to have loading in say 2 or 3 different directions. So we are going to have normal stress sigma x, we are going to have normal stress sigma y, and if we are talking of 3D, then we will have normal stress in z direction also, which is going to be sigma z. However, we will be restricting our study to 2 dimensions only, so we will be talking about biaxial loading. So we will have sigma x and sigma y. We will be talking about plane stress situation. So in plane stress, all the stresses are going to be within one plane. So there is no component of stress in the z direction. We don't have any stress in z direction, whether it can be whether it is normal stress or shear stress. There is no stress in z direction. Before we start our chapter 7, let me just briefly go over this problem 6.9 that we solved in beam shear. Now, as I said that if you were to find the value of Q, you can either consider if we are to find the value of shear stress at a point A on the cross section. So I said that you can either consider the portion of the cross section above this point, or you can consider the portion of the cross section below this point. Both are going to give you the same value of Q. Let me just elaborate that a little further. We have already done the upper portion in the solution of the problem. Now when we consider the bottom portion, that is below point A, I have drawn it separately here. So let us consider a point B which is at the same distance from the bottom surface as point A is from the top surface. That is, it has 1 inch distance. This distance is also 1 inch. So this portion which is below point B is same as portion that we have above point A. So these two are exactly same. Now when we take moment about the neutral axis, when we take moment of the area vector about the neutral axis, then remember Q is integral y dA, so that is first moment of area, y dA. So when we take the first moment of area about the neutral axis, then we have to consider the direction of the moment also. If we consider a portion of the cross section in which neutral axis is not there, like we considered the top portion above point A, so there was no problem because we didn't have neutral axis in that portion. However, if we consider the portion of the cross section below point A, then we have neutral axis in this. So if neutral axis is there, then the area vector above the neutral axis and area vectors which are below the neutral axis, they are going to produce moment in different directions. So when they produce, area vector is perpendicular to the plane that we are looking at, and perpendicular to the plane of the cross section. So when both the area vectors say for these two regions A1 and A2 is the region from point B up to the neutral axis. So these two regions, they have the same area, their location of their neutral axis for each one of these two, A1 and A2, with respect to the neutral axis of the complete cross section is also identical. They are identically located with respect to the neutral axis of the complete cross section. So the moment produced by this area vector A1 and moment produced by this area vector A2 about the neutral axis of the complete cross section is going to have same magnitude, and both are going to be in the opposite directions, so they are going to cancel the effect of each other. So net moment produced by this portion between A and B, the net moment produced by the portion between A and B is going to be 0. So only the portion which is below point B is going to produce moment about the neutral axis. Net moment is going to be that which is going to be same as the moment produced by this portion above point A about the neutral axis. So in that way, the two portions will have same value of Q. So it is always safe to consider the portion in which you do not have the neutral axis. So in this case, if you just consider the top portion, that is going to be safe. Otherwise, you have to consider the direction of the moment produced by different area vectors, because different area vectors, when you have neutral axis in between, about the neutral axis, different area vectors in this case are going to produce moment in different directions. So that is why the value of Q is not going to change. Now we go to chapter 7 of the book. This is chapter 7, transformation of stress into strain. So we are going to transform the stresses from the planes on which we know the stresses, and then we are going to find the stresses on other planes. So in general, we can have three-dimensional stress system like this. So sigma x, this is the x direction, this is the y direction, and this is the z direction. So this stress, normal stress, is going to be sigma x, this is going to be sigma y, and this is going to be sigma z. Similarly, this is going to be tau xy, because x is the direction of the outward normal and y is the direction of the shear stress. So this is tau xy. In this case, again, outward normal is along x, so first subscript is x, and the direction of the shear stress is along z, so this is tau xz. Similarly, this is tau yx, this is tau yz, this is tau zy. The first subscript is the direction of the outward normal, which is along z, and the second subscript is direction of the shear stress, which is along y, so this is tau zy. Similarly, this is tau zx. So this is a three-dimensional stress system in general, and we are going to transform these stresses to, say, some other x system, say x bar, y bar, and z bar, z prime, x prime, z prime, x prime, y prime, z prime. However, we will be restricting our study to plane stress. Plane stress means that all the stresses are there in a plane only. So in that case, we will assume that plane to be xy plane, so there is no stress in the z direction. So sigma z and this shear stress, which is tau xz, or this shear stress, which is tau yz, all these are going to be equal to 0. So we will have sigma x, sigma y, and tau xy only. So let me show you this on a separate figure, because here it is not very clearly shown. Actually, this is now we are talking of plane stress. So we have this sigma x, and we have only tau xy on this face. The other shear stress is going to be in the z direction, so that is going to be 0, because there is no stress in z direction. the other stress possibly which can possibly be there on this plane, shear stress, that is going to be tau xz, so that is going to be equal to 0. So on the horizontal plane at the top, this perpendicular to this plane is y-axis, so this is going to be sigma y, and this is going to be tau yx, which is, since it is equal to tau xy, so he has just used 1 tau xy. And now we would like to find the stress on a plane, on an oblique plane, which is making some angle with this, say, vertical plane or with this horizontal plane. So say we rotate the axis through an angle theta. So with respect to x-axis, this is the angle theta. So our x prime axis is going to be this. So y prime axis is going to be this. Z prime axis is not going to change because we are rotating within the xy plane. We are talking of plane stress, so we are just rotating in the xy plane. So z prime is still going to be same as the original z. Now we would like to find what are going to be the normal and shear stresses on this on these oblique planes, which is this one, which is making an angle theta with the vertical plane, and this one, horizontal plane, which is making an angle theta with the original horizontal plane. So let me show you a figure that I have made myself. This one. Now this is the angle theta. This is the angle theta made by the x prime axis with the original x-axis. This is the x-axis, this is the y-axis, and those shown with the red are the new axes, x bar and x prime and y prime. I have just drawn a plane figure so that will probably be easier for you to understand. So we make a rotation through an angle theta, so our sigma x prime is going to be along this, and tau x prime y prime is going to be in this direction. Now we are just considering this triangle. So say this is one portion of the cube that we had in the figure of the book. So this is just one portion of the cube. So we consider the area on the oblique plane equal to delta A. It is not very clearly visible here. This is delta A. This area of the oblique plane is delta A. And since this angle is also going to be theta, since this angle is theta, so this angle is also going to be theta, and these two angles are equal from geometry. So this angle is also theta. This one it is equal to this angle. So if this area of the oblique plane is delta A, then area of this plane is going to be delta A cos theta, and area of this side is going to be equal to delta A sin theta. Just taking the component of this side with this, the other dimension will remain same. Let me show you the figure of the book again. Let's see this one. So we are considering this portion of the triangle, this portion. So we are going to have, if we rotate this through some angle, then the oblique plane is going to be making some angle with the vertical plane, or if we are talking of the top plane, then the oblique plane is going to be making some angle with the top plane. So now what we do is that we just consider a segment, a portion of this beam which is making an angle theta with the, say, vertical axis. So we are considering just a portion of this. We are we are slicing uh, the cube like this, and this angle is going to be theta. So instead of showing this three-dimensional figure, we are just looking at the two-dimensional figure. So this area of the oblique plane is delta A, so area of this side is going to be delta A cos theta, area of this side is going to be delta A sin theta. Now the stress acting on this vertical, this is the vertical plane, this is the horizontal plane, this is the oblique plane. This is the vertical plane, this is the horizontal plane, and this is the oblique plane. This is the, you can say, front view of the portion of the cube. So this is actually your oblique plane, this is your vertical plane, and this is your horizontal plane. So the stress acting on the vertical plane was sigma x. So we multiply sigma x, we draw the free body diagram. We draw the free body diagram and then use the equilibrium equations to find the value of sigma x prime and tau x prime y prime. Now, since in the free body diagram, when we apply the equilibrium equations, we are not talking of stresses in the equilibrium equations, we are talking of forces. So we need to convert all these stresses to forces. So we are going to multiply each stress with the area over which it is acting. Now, say this stress sigma x prime is not known to us, it is acting over an area delta A, so we just multiply sigma x prime with delta A. Similarly, this shear stress which is acting on this oblique plane tau x prime y prime, it is acting on an area delta A, so we multiply tau x prime y prime with the area delta A. This is the force in this direction, this is the force in x prime direction, this is the force in y prime direction. This normal stress on the vertical plane is sigma x. So we multiply sigma x with the area over which it is acting, which is delta A cos theta. So sigma x multiplied by delta A cos theta. Similarly, the shear stress on this side is tau xy. So again, tau xy is going to be multiplied with delta A cos theta. It is acting over this area. On the bottom face, on this face of the triangle, this is actually the horizontal plane, and perpendicular to this is the y-axis. So the stress is sigma y. Sigma y is acting over an area delta A sin theta. So we multiply sigma y with delta A sin theta. Similarly, the shear stress is going to be equal to tau xy on the horizontal plane. Actually, it is tau yx, but he is just using in the book as tau xy because tau yx is going to be equal to tau xy. So we multiply the shear stress tau xy with the area over which it is acting, which is delta A sin theta. So now we have converted all the stresses to forces by multiplying the stresses with the corresponding areas. Now we sum the forces in x prime direction. We sum the forces in x prime direction. Summation fx prime is equal to 0. So this force is already in x prime direction. So we have sigma x prime into delta A minus component of this. It will have two components, one component in the negative x prime direction and the other component in positive y prime direction. So these are going to be the two components of this sigma x into delta A cos theta. This is the force. So we have to take component of this force. So component of this force along the x prime direction, the angle is going to be theta. The angle is going to be theta. This angle. So sigma x delta A cos theta into the component along x prime, angle made with x prime is theta. So the component is going to be sigma x delta A cos theta into cos theta, and this component is going to be in the negative x prime direction. So we write a negative sign here. So the component of this force, sigma x into delta A cos theta along x prime direction is this. Similarly, the component of this tau xy delta A cos theta, tau xy delta A cos theta, this is the force, and the component along x direction, this angle is going to be theta, so cos theta is going to be in the negative y direction and sine theta is going to be in the negative x direction, component of this force. So we have tau minus tau xy delta A cos theta into sine theta. This is the component of this force in the x prime direction. We are just resolving all the forces. We are just taking the components of all the forces in x prime direction. Now we talk of these two forces, sigma y into delta A sine theta, this force, the component of this is your x prime direction and this is your y prime direction. This angle is going to be theta, this one. So angle with y prime direction is going to be theta. So x prime component is going to be this force into sine theta, and the component is going to be in the negative x prime direction. One component is going to be in the negative y prime direction, the other component is going to be in the negative x prime direction. So the x prime component is going to be sigma y into delta A sine theta into sine theta. So this is the component in x prime direction. And lastly, this last force minus tau xy into delta A sine theta, this is the force and its component, it is going to make an angle theta with the x prime direction. So, and the component is going to be in the negative x prime direction. So the component is going to be minus tau xy delta A sine theta, this force, into cos theta, and component is going to be in the negative x prime direction. So this is our equation in x direction. This is the force equation, equilibrium force equation in x direction. Summation fx prime equal to 0. As you can see, delta A will cancel throughout the equation. All the terms have delta A in it, so we can divide the whole equation by delta A. And since we have to find sigma x prime, so we move all other terms to the other side. So delta A is cancelled, so we are left with sigma x cos square theta, and this will also become positive on the other side. This is sigma y sine square theta, and these two are same. Tau xy delta A cancels, tau xy sine theta cos theta, tau xy sine theta cos theta. So this becomes plus 2xy sine theta cos theta when we move it to the other side. Now we will use the trigonometric relationship. Cos square theta is equal to 1 plus cos 2 theta divided by 2, and sine square theta is equal to 1 minus cos 2 theta divided by 2. And this 2 sine theta cos theta is equal to sine 2 theta. Now we can just rearrange the terms. We can combine the terms involving theta, write them separately, and we can write the other terms separately. So we have sigma x divided by 2 plus sigma y divided by 2. So this is sigma x plus sigma y divided by 2. Then sigma x into cos 2 theta divided by 2 minus sigma y into cos 2 theta divided by 2. So this becomes sigma x minus sigma y divided by 2 into cos 2 theta plus this term. So this is our expression for sigma x prime. Sigma x prime is going to be equal to this. Similarly, we can sum the forces in y prime direction. Summation fy prime is equal to 0. Y prime direction is this. So in y prime direction, we have this force, tau x prime y prime into delta A. Then component of this, it was making an angle, component of this force, it was making an angle of theta with the x prime direction. So along y prime direction, is component is going to be in the positive y prime direction, and that is going to be sine theta. So the force sine into sine theta, and component is positive. Then the component of this, it is making an angle theta with the y prime direction, and component is going to be in the negative y prime direction. So this force into cos theta, tau xy into delta A cos theta into cos theta. Cos theta is going to be the component because angle made with the y prime direction is theta, and the component is going to be in the negative y prime direction, so this is negative. Similarly, the component of this in the y prime direction, it is making an angle theta with the y prime direction. Component is going to be in the negative y prime direction. So minus sigma y delta A sine theta, which is the force, into component is going to be cos, because angle is made with the y prime direction, theta angle. So it is cos theta. Then the component of this force, it is making an angle theta with the x prime direction, and component in y prime direction is going to be in the positive direction. So plus tau xy into delta A sine theta, and the component is going to be sine theta. So we write another sine theta here. Again, we can divide the whole equation by delta A. So delta A will cancel throughout the equation, and we can now move all of the terms onto the other side. So we have tau x prime y prime is equal to minus sigma x into sine theta cos theta, and plus this is sigma x sine theta cos theta, and plus sigma y sine theta cos theta, and we have this plus tau xy, and this is cos square theta. This will become plus on the other side, this will become negative. So cos square theta minus sine square theta. Now we can just take minus common here, and we can divide and multiply with 2, so that we can use the relationship 2 sine theta cos theta is equal to sine 2 theta. So we have just taken negative common, so this becomes sigma x minus sigma y into sine theta cos theta, and we are dividing this by 2 and multiplying this with 2. So now this can be written as sine 2 theta, and this term remains as it is. Cos square theta minus sine square theta is equal to cos 2 theta, so we just keep it like this. So this is our expression for tau x prime y prime. So this is how we are going to find the normal and shear stresses on an oblique plane. On an oblique plane, when the stresses on vertical and horizontal plane, which are sigma x on the vertical plane and sigma y on the horizontal plane at the top, when those are known to us and we want to find the stresses on an oblique plane which is making an angle theta, then we can use these relationships to find the normal and shear stress on that oblique plane. So we are going to transform the given stresses to a plane which is making an angle theta with the x or y direction. So how much time we have taken? It's already going to be about 30 minutes. Okay, so we can stop here. Actually, now what we have to do is that we are just not finding the stresses because we would like to find the stresses on an oblique plane. We have to find the maximum normal stress and maximum shear stress which is going to be applied. Maximum normal stress and maximum shear stress to which the structural member is going to be subjected to, because those stresses are going to be important for us from design point of view. So we are going to use these relationships to find the maximum stress and the location of the maximum stress, that is on which plane, what is the angle made by that plane with the x or y direction, with the horizontal or the vertical plane, what angle is going to be made by the plane on which we are going to have the maximum normal stress and the plane on which we are going to have the maximum shear stress. So we are going to use these relationships to find the maximum normal and maximum shear stress. That we'll talk about in the next lecture. That's all for this lecture. Thank you.